Welcome to Empowered Learning. This video will be an extension of the video I've made on solving second order linear homogeneous equations, differential equations with constant coefficients. So now we're going to talk about solving higher order homogeneous ordinary differential equations with constant coefficients. And so the purpose of this video is really to remind you of the factoring techniques that you've learned in, let's say, a college algebra or a pre-calculus course that actually apply to helping us be able to solve these types of equations. And so what I'm going to do here is we will first talk about the theorems that go along with solving these types of equations, just to kind of let us know based upon the characteristic equation outcome, what our general solutions will look like. And then from there, we will do a few examples just to kind of give you an idea of how all this works. Again, the main point of this video here is to expose you on how to deal with a higher order, nth order homogeneous ordinary differential equations with constant coefficients, with the key in mind to remind you of some factoring techniques that you may have forgotten. All right, so as I mentioned before, we're really just trying to solve these differential equations by essentially dealing with the characteristic polynomial or characteristic equation. And so the factoring techniques that I want to bring back to your memory here are of course, your traditional factoring. That's by trial and error, factor by grouping, or some of you may have known divide and squeeze. Completing the square, whenever we have to factor something by an irreducible expression. So let's say, for instance, if I had x squared minus x plus 1, that is something that I can't factor out normally during the traditional methods. So I could use completing the square to make this look like, and I'll just go ahead and do it here. This will look like x minus 1/2 quantity squared here, and this will be like minus 3/4. So by doing the whole completing the square method this way, and if you've forgotten that, hope I got this right mentally here, but basically we take whatever number this is, which is an understood 1, we divide it by 2, and then we square it. And what we try to do is force this to be a perfect square here, plus or minus some other number. So here we essentially say I'm going to rewrite this as x squared minus x plus some number. And then of course, since I have a plus 1 here, to balance everything out, I have to subtract by that same number. And so here, if I take the negative 1 divided by 2 and square it, that's going to be a positive 1/4. So I would have a positive 1/4 there. And of course, what I have here automatically factors into x minus whatever I have inside the parenthesis here, quantity squared. So that's always true, no matter how ugly the number looks. And then of course here, if I just take 1 and subtract it by 1/4, I get 3/4. So that's how I got that. And so we'll be seeing some instances where something like this will actually come into play and helping us out. Of course, the last one here, which is probably what I call the sexiest one of all, would be the rational zeros theorem. And so this theorem you learned, or you may have learned in the college algebra or pre-calculus course, that basically gives you a quick way to try to figure out if a polynomial of high degree can be factored down by finding its corresponding rational number zeros, or zeros that look like fractions. And so as long as our polynomials have all rational number coefficients, then this theorem has potential to help us to be able to find the zeros for that polynomial and essentially factor it down by using synthetic division. Okay, so those are the things through example that I am going to try to put into these examples to help you remember that and see the connection in between remembering that stuff and how to solve these equations here. So what I want to do now is move on and let's talk about the three theorems that we need to talk about, and so that we can kind of get an idea of what those are. Please know that if you've watched my video on reduction of order, or if you watch my video if you've watched my video on solving second order linear homogeneous equations with constant coefficients, this is going to seem very familiar to you. It will just be an extension of what we already know for the case 2 and case 3 situations for those topics. All right, so our first theorem, it says, let R be some root of multiplicity m for this characteristic polynomial here, okay? So I'm going to kind of do this by example as I go along. So let's say I have something like this. So I got x squared plus 6x plus 9, okay? And matter of fact, let me change these x's to r's right quick. Right. So we know that this particular quadratic could be factored to x plus 3 quantity squared, okay? And so because of that, what this tells us, if I set this equal to 0, then it means r plus 3 is equal to 0, which r is equal to -3. So circle this again. So because we know that our root to this quadratic equation here is -3, and it came from an equation where we had one factor, and that one factor was repeated. In other words, we had 2 of the same factor. Then this lets us know that this particular root has a multiplicity of 2. So it means it came from a factor that repeated twice in the quadratic, or in this case, characteristic equation. Now, how that's tied to this theorem here is, if you remember, for second order linear homogeneous equations, imagine that we had the equation y double prime plus 6y prime plus 9y equals 0, okay? Then, of course, this would be the characteristic equation for that particular equation. And because of the fact that we only had one distinct solution to come out, we know that for our basis, e raised to the -3x would be the first general solution. But via reduction of order, we know that the second one would be x times e raised to the -3x. And both of these functions will complete our basis for this second order linear homogeneous equation, okay? Now, what theorem 1 is basically trying to communicate is what happens if this second order was a 4th order or 5th order or 6th order, okay? And so to put it briefly here, if I had a 3rd order ordinary differential equation, so I'm not going to write everything. So let's just say I had something that looked like this, and let's say we had something with a y in it. Then here, when we figure out what the roots of this particular, of the characteristic equation for this equation would be, if we had something that was, let's say, r plus 3 cubed equals 0, then of course this means that r equals -3 would have a multiplicity of 3. Thus, our general solutions, our fundamental functions for our general solutions that complete our basis would end up being these 2 functions, but also this one, okay? And so notice that with 3rd order differential equation, if we have a situation where we only have one distinct solution from our characteristic polynomial, that means that that particular root is of multiplicity 3, which means we have 3 distinct functions for our basis. And remember, reduction of order allows us to use this particular solution to get this one. And if we did reduction of order again, we would get this one, okay? Now, the whole purpose of theorem number 1 is to obviate the need for you to have to do reduction of order over and over and over and over again. Okay, so we kind of know what the pattern is going to be. So let's say if I had a fifth order ordinary differential equation of this type that was homogeneous, then here I would have this, and I would keep on going until I got to, let's say, x to the fourth e to the minus 3x, and I would stop there. Okay, and so that's really what this theorem is trying to communicate. So it says, again, let R be a root of multiplicity m for the characteristic polynomial for this particular equation here. Of course, all of your a sub zeros, a sub ones are constants. Then this particular set will form a basis of solutions that are based upon this particular root. Okay. Now, one thing I do want to mention here is that let's say the characteristic equation has more than just this root. Okay, but let's say it looks something like this. So let's say it has something like this. Okay, so let's say that your characteristic equation ends up looking like that. Well, here we have r equals 3, which has r equals negative 3, which has a multiplicity of 4. And on top of that, we have r equals 2, which has a multiplicity of 2. So for this particular root, we would have the basis functions e raised to the minus 3x, x times e raised to the minus 3x, x squared e raised to the minus 3x, and x cubed e raised to the minus 3x. Okay, and so we always stop one number short of the multiplicity here with the powers for x. So this would form a basis of solutions for this root. For this one, since it is just of multiplicity 2, we would have e raised to the 2x and x times e raised to the 2x. Just like we did whenever we had case 2 of second order linear homogeneous equations. And so our general solution would be a linear combination of all of these. Okay, so that is what theorem 1 is essentially trying to communicate. All right, let's move on to theorem 2. So theorem 2 is basically trying to extend what we know about the case 3 situations for second order linear homogeneous equations. Okay, so again, we know for case 3, we would have situations where, let's say, let's say our characteristic polynomial ends up being something like this. So let's say r plus 3 squared plus 1 equals 0. Okay, so let's say for whatever reason we have a differential equation, and this is the characteristic polynomial for it. Of course, if we were to go and solve for the roots for this, then this is going to be r plus 3 quantity squared minus 1. And because anything squared equals a negative number, you know it's going to be complex, then this will end up being r plus 3 is plus or minus square root of 1, which of course we know is plus or minus I. And we know r would essentially end up being a negative 3 plus or minus I. Okay, and from that, if you remember, our general solutions for this, well, I'll say the basis of solutions for this would be e raised to the minus 3 plus or minus I x. And of course, we could do the plus or the minus. So if we looked at it that way, this would be this plus I x. And then the other solution would be this. But remember that we didn't like it in this form because this is a complex solution and we're using these equations to model real valued things. So using Euler's formula here, So if you remember here, e raised to the I theta is just going to be cosine of theta plus I sine of theta. And what this ended up being here is that we could rewrite our solutions in terms of sine and cosine, okay? And to be specific about it, I'm going to write up here, our general solution would be e raised to the lambda x times cosine of omega x plus, well, actually this will be C1 times cosine of omega x plus C2 sine of omega x. And this is where our roots end up having the form of lambda plus or minus omega I. So the -3 here would be the lambda in this case, and the understood 1 next to the I here would be the omega in this case. Okay. So the point that I'm trying to make here is, if you remember this from the case 3 situation for a second order linear homogeneous equation, if we had a third order, a fourth order, or a fifth order, all we're doing is extending that, okay? And so we want to avoid having to do the reduction of order. And so since we already know what the pattern is, if we had it for a second order, and let's say our root here, whatever this ended up being, it was the only root for it, and it had a multiplicity of 2, then we kind of know what to expect. Just like how we did for theorem number 1. So now that we've kind of got that reminder here, I'll go ahead and read this again. So it says, consider the same ODE as we did in theorem 1. The characteristic equation for the characteristic equation root R of multiplicity M and the basis of solutions here. Okay, so all that we're still considering. So if R ends up being a complex number, or a complex root in this case, then it must be true, of course, that its conjugate is also 1. And that's what I was talking about here. Now, we also know that if our roots end up being complex and they are a multiplicity M, then, of course, the basis for which we're going to get our general solutions are going to naturally come from this set here, okay? And so it's just like how we did for theorem 1, but instead of writing just x e raised to a real number x, then of course we would have, x raised to a real number times e raised to a real number x. Then we have x raised to a real number times e raised to a complex number times x, okay? And we just expand that out. And so this first thing that I've boxed here goes along with, let's say, this particular complex number, whereas the one that I've boxed here will go along, oops, let's get rid of that, will go along with the conjugate. So this one goes here, this one goes there, okay? Now, remember, we have all the basis of solutions, we have it in a complex form, which is not useful to us, okay? So since it's not useful to us, we want to rewrite everything in the form of having all real functions. And so if you remember, when we covered this, we took Euler's formula here and essentially said that, all right, I want to add these two together and see what I get. And then I want to take the difference of these two and multiply it by I and see what I get. And in this first case, I ended up getting just a cosine function. In this case, I ended up getting a sine function, okay? And from that result comes theorem number 3 here, okay? So since we know, if we're considering the same situation as theorem number 2, since we know from this, we could express our general, how do I want to say this? We want to express our fundamental set of, or basis of solutions just in terms of real numbers here, which we know we could do it this way, then of course we can also change the basis of solutions from looking complex now to just looking real, where we express everything in terms of a cosine and sine function. Okay, and so this is what it would look like for the r equals lambda plus omega I roots. This is the corresponding basis of solutions for that, depending upon the multiplicity of this root. And this one would be its conjugate. The root of this goes along with these basis functions for the basis. And we also see here that it could have same multiplicity as this one. Okay. And so because of that, what we end up with is a linear combination of these types of functions here to express our general solution. Okay. And so I know that, again, we go over these theorems and we're kind of talking high level here. I am going to do examples to try to explain practically what that actually looks like. But I'm going to be referring back to these three theorems here as we go along through our examples so that we can hopefully make those connections. All right, so let's get into the actual examples now. All right, so here is our first example. And so we see that we have this fifth order linear homogeneous ordinary differential equation. Okay, we know it's fifth order because the highest derivative is 5. We know it's homogeneous because it equals 0. And we know that is linear because, of course, we got a fifth order derivative raised, well, a fifth derivative term, a fourth derivative term, third derivative term, so on and so forth, all the way till we get to the no derivative term. Okay. Now, because of that, we know that this particular equation has a characteristic equation that ends up just being r raised to the 5 plus 10 r raised to the 4 plus 40 r raised to the 3 plus 80 r raised to the 2 plus 80 r plus 32 equals 0. Okay. Now, at first glance at this, you're like, how in the world am I going to factor this out? And that's a good question to ask. Now, how we're actually going to do this is we remember we don't have any standard kind of silver bullets for anything that's above the third order as far as polynomials are concerned and factoring them down. So we use the rational zeros theorem to help us out here. Okay. And again, what the rational zeros theorem basically says is that if I have a polynomial, which I do have here, and all of my coefficients here can be expressed as fractions. So that's what they mean by rational zero, or it's just rational number in general. So if all my coefficients here can be expressed as fractions, or they are rational numbers, then I could figure out a possibility of numbers that could actually be zeros for this polynomial, meaning numbers that I can plug in for r to make this thing go to 0. And what that grab bag of possibilities is going to look like is going to be a combination of plus or minus all factors of the last term, which is in this case going to be 32, divided by plus or minus all factors of the first term, and in this case it's going to be understood 1. Okay, so here I know that all the factors are 32. I got plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, plus or minus 16, plus or minus 32. Okay. Now, all the factors of 1 are just plus or minus 1. And so since I only have one denominator here, of course, 1 divided by everything is just going to be the same stuff here. So I don't really have to write this denominator here. I can just say it's going to be the list of everything I have in the numerator. So we'll get rid of the denominator here and then move forward. All right, so from this point, this is the list of possibilities that I could use to plug in for R here to figure out which of these are going to be 0, if any, okay? The rational zeros theorem does not guarantee that any of these numbers will work, but it does say that if you have a number that you can plug into this polynomial that will make this polynomial go to 0, and it is a rational number, it will have to come from this list, okay? Now, it turns out for this particular problem here that if you try out all of these numbers here, the only one that ends up working is going to be -2, okay? And so what I'm going to do is show you a way to use your graphing calculators to actually figure this out, okay? Relatively simple. Now, depending upon if you're just trying to learn this for yourself or if you're taking a course, you may or may not have the option of using a graphing calculator. And then, of course, there's other means to do it. If you're forced to not use a calculator, then the process will be longer, but you can still do it, okay? But I am going to use this just in case you are able to use a graphing calculator, just to kind of help you out here. All right, so I'll pull my graphing calculator in, and what I'm going to do is go ahead and type in this characteristic polynomial that I have here. I'll get it out the way for a second. Yeah, I'm going to type in this characteristic polynomial here. And then after I do that, then we'll try these out to see which ones actually ends up being zeros or not. And you'll see that -2 will be the only one. All right, so I'll go ahead and type this in now. So we'll go to the y equals button here. And then I'm just going to type in this, and I'm just going to replace all these y's with x's. That's probably the easiest way that I can do it here. So we'll say x raised to the 5. And then this will be 10 times x raised to the 4. And I'll just continue typing these in. Okay, so I have that typed in. And so now for my list, remember that, and I'll get rid of this again. So remember that here, my list are numbers that are basically in between -32 and +32. So here in the window here, I want to make sure that my x-min and x-max could actually fit every number from -32 to +32. So I'm just going to choose from -40 to 40 just to give myself a little room. And then from there, I'm going to use the calculate feature to figure this out, okay? So I'll hit second, calculate value. And then from here, you see where the x is. And what we're going to do is just type in those numbers here, okay? So I'm going to scroll down a bit so that we can actually see the numbers. So these are the numbers that I'm going to try out. So I'm just going to go, first one is 1. We see that does not equal 0. -1, see it doesn't work. And I'll try -2. And there must be something, oh yeah, I typed something wrong there. Let me go back and fix that. So let's see here. Yep. Yeah, that should be a plus. All right. So that should be, so we'll go back to calculate. We'll try that again. Yeah. So here, of course, 1 doesn't work. -1 doesn't work. -2 does work. And so that's what I was talking about. So this is a quick way to let your graphing calculator run through all of these zeros here. Now, of course, if you're looking at the graph here, you can see that the only place where it crosses is here. So that's another thing that could, help you out. But just in case you can't see the whole entire graph, and I normally go through this just because we may have a graph that will come up here and then bounce back down and come back up. You never know that. So I don't trust that. So I just run through the numbers. So that's why I'm doing this. So again, if we go with 4, doesn't work. -4 doesn't work. -8 doesn't work. 8 doesn't work. 16 doesn't work. -16 doesn't work. And of course, 32 and -32 are not going to work either. Okay. So we see, of course, that what this graph looks like is essentially what it is. And we see that the only rational zero that did work is a -2. So we're going to take note of that and move forward in this problem. So now from testing here, testing the rational zeros, we find out that r equals -2 is the only actual rational zero. Okay. Now, one thing I do want to warn you of, just because this is the only actual rational zero does not mean we can automatically jump here and assume just because this is, of order 5 type of equation, which means we have a 5th order, a characteristic equation of the 5th degree, that we can just automatically assume that, boom, this is going to be, all this is going to factor to that. Okay. We can't assume that. In this case, this is what it's going to turn out to be, but we cannot assume that. Okay. Part of the reason is that whenever we apply this rational zeros theorem, this comes in what I like to call singles. So this could very well be a root of multiplicity 1, and the other 4 zeros could possibly come from a polynomial expression that could factor into two quadratic factors where we have conjugate irrational pairs, or we have 2 complex conjugate pairs. Okay. So the reason of me stating this is that after we figure out what our rational zeros are, we really do need to go and test to see how is that going to actually help us factor this down. And we're going to use synthetic division to do that. All right, so I'm going to erase this and then we'll actually start that process. All right, so now using synthetic division, I'm going to set up this polynomial here to do it. So I'm going to use all the coefficients from my characteristic equation here. I'm going to set it up this way. I have 1, and then 10, then 40, then 80, 80, 32. Then I write what is called my remainder box here. I put my number that's going to be a 0 here. And how I start this process off is I take whatever number is here, I pull it down, and then I do a succession of multiplying and adding. So I do -2 times a +1 is a -2, then I add. I repeat, -2 times +8 is -16, then I add. Repeat, -2 times +24, -48. And then I just keep on going. So this will be 32, and then -2 times a positive 32 is going to be 64, or -64. And then that is 16. And then, of course, -2 times 16 is -32. That's 0. Now, 0 is what we want here. The reason why we want that is because of the fact that one of the things that we know about using synthetic division is this thing called the remainder theorem. And the remainder theorem says that, hey, if I take a polynomial like this and divide it by a linear factor, and what I mean by that is this is essentially saying, it's the equivalent of saying, I want to take this polynomial and divide it by r plus 2. If I see that this actually contains a factor of r plus 2, then the r plus 2 that is in here divided by the r plus 2 that's here will reduce to 1. Okay, and because of that, you'll end up having a remainder of 0. Now, what the remainder theorem basically says is that whatever number you get here is the same as evaluating this function at whatever 0 you have. Okay, or the potential 0 that you have, right? So whatever this number is here, if I let this be f of r, then f of whatever that number is what gets in this remainder box. And of course, I do want a 0 here to show that this indeed is a 0 of this function. Now, what this means to us is that now this tells me that I could rewrite this if I wanted to name, let's say, this f of r, then I could say that f of r, let's try to write that again. So let's say f of r here is now r plus 2 times something else, okay? And it just so happens that that something else is actually down here, okay? Now, notice that we went from a polynomial of degree 5 divided by a polynomial of degree 1, and that's what that representation is here. And what this is going to be is a polynomial of degree 4 as a result. And my quotient that I have here is really the coefficients of that particular polynomial that remains. So this ends up being r raised to the 4 plus 8r cubed plus 24r squared plus 32r plus 16. Okay. And so we know from this that this could be factored down to that. Now, because this is the only rational 0 that I have, I want to see, well, how big is the multiplicity of it? Okay. So what I need to do is I need to do this process again. So to do that, what I'm going to do is going to set this up the same. But this time, instead of using these coefficients, I'm going to use what I have here in the next round of synthetic division. Set up my remainder box, pull down this number, and I go through the process again. So if I do that, negative 2 times positive 1 minus 2, add. Negative 2 times positive 6, negative 12, add. And then I'll just go ahead and write the rest here. Yep, so I got that. And then that ends up being 8. And then negative 2 times positive 8 minus 16, 0. So again, we know that this works. And what this tells us here is that f of r now is r plus 2 times r plus 2, or r plus 2 squared, times, and then here, remember, this is a polynomial of degree 4 divided by a polynomial of degree 1, which leaves me with a polynomial of degree 3 in the quotient. And so now I could rewrite this as r cubed plus 6r squared plus 12r plus 8, okay? And so now at this point, again, we know that since we went down from 5 to 3, we know that this r that we had up here has at least a multiplicity of 2, okay? We're going to do one more round of this. And so I say one more round because if this works, I know that what I'm going to get as a result in the quotient this time is going to be a quadratic equation. And of course, we have ways of finding the zeros for a quadratic equation or factoring out quadratic equations. So again, I'm going to take these coefficients here, use them down here. Pull this down. Minus 2 times 1 minus 2, add. Repeat, negative 2 times positive 4, negative 8, add. And then negative 2 times positive 4 is negative 8, add. And so now this shows me that my characteristic equation can now be rewritten this way. Okay. So now at this point, notice that what I have here in the second factor, which is r squared plus 4r plus 4, all this is r plus 2 raised to the 2. So this is what lets us know here that our characteristic polynomial is really just r plus 2 raised to the 5. Okay. Now, we see that we know this. So I know that r equals negative 2 is a root of multiplicity 5. So what that tells me in terms of my general solution to my differential equation, my basis of solutions here, I know that since this is a linear homogeneous equation and I'm really extending the case 2 situation from the second orders, I know that r equals negative 2 here, I'm going to write this up here, translates to e raised to the minus 2x as my first general solution. But now, because I have a multiplicity of 5, what that means is I also have x e raised to the minus 2x as another one, x squared times e raised to the minus 2x as another one, x cubed times e raised to the minus 2x as another one, and then finally I have x to the 4th e raised to the minus 2x. So all of these functions that are linearly independent of each other are going to be the basis of solutions for this particular differential equation. And so if we go back to theorem number 1 here, it's exactly what I'm stating here. So we're just using what we know. We had a differential equation of this form. All of our constants, all these coefficients here are constants. And since they were rational numbers, we could use a rational zeros theorem to help us out. Here's our basis of solutions here, okay? And because that is our basis of solutions, this tells me that my final general solution for this particular equation is just going to be C1 times e raised to the minus 2x plus C2. Let me back up there. C2 times x e raised to the minus 2x plus C3 x squared e raised to the minus 2x plus C4 x cubed e raised to the minus 2x and plus C5 x raised to the 4 e raised to the minus 2x. So this would be your general solution to the differential equation. Okay, and again, I know it seemed like we did a lot, but once you actually kind of go through these steps here, you'll see that as long as we have the factoring part down with the rational zeros theorem, this problem is actually relatively easy and it's relatively quick to do. Okay, but again, you have to be familiar with the whole rational zeros theorem thing to be able to do that. So again, this is our general solution to this differential equation here. All right, we'll move on to the next example. All right, so for the next example, similar situation here, but now we notice that our characteristic polynomial is going to look different, okay? We do have a third order linear homogeneous differential equation here because we do have a third derivative term. Of course, we're missing a second derivative and a first derivative term, but that just implies that those terms are just 0 plus that function raised to those corresponding derivatives. And of course, we have a term that doesn't have a derivative in it and it equals 0. So this fits the profile of the type of equation that we're looking at. Our characteristic equation here, based upon that, would just be r cubed minus 27 is equal to 0. Okay. Now, if we have this, then of course, this is the same as r cubed minus 3 cubed. And I write it this way because we have the sum and difference of cubes as a factoring technique or a factoring identity that we could use. Okay. And in general, if we have a cubed minus b cubed, we know that's going to be a minus b times a squared plus ab plus b squared. Okay. And if we have, let's see, a cubed plus b cubed. Oh, actually, that's not right. Let me go ahead and write this one first and then I'll change it. Let's see, that's this. Yeah, so that should be it. Yeah, so this is right. Yeah, I thought I had let's make that this. Yeah, so whenever it's minus plus plus, and whenever it's plus, then it's plus minus plus. So here we see that this fits the profile of this one. So this means that I would have r minus 3 times r squared plus 3r plus 3 squared, which is 9. Okay, and that would equal 0. So from here, we see that either r minus 3 is equal to 0 or r squared plus 3r plus 9 is equal to 0. Okay. So now at this point, of course, we know here that this means that r is just equal to 3. So that's an easy root that we can come up with. For the other two zeros, corresponding zeros here, this is not something that we can factor easy. So we could either use the quadratic formula or we could use completing the square. Since I mentioned completing the square, I'm going to use that just as a way to work this out. But again, you could perfectly use the quadratic formula if you want to. So for here, well, I'll just work it down here. So for this, I know that if I'm going to do completing the square, I need to come up with a term here, add 9, and then either I could subtract 9 on this side of the equal sign or just add it on this side. So I'm going to elect to just add whatever that's going to be. And I'll get rid of this. So here I know that to do the completing the square, I got to take whatever number this is. I need to divide it by 2 and square it. And same deal here. Okay. And so if I do that, then this over here will automatically factor into r plus 3 over 2 quantity squared. And this will just be 9 over 4. So I'll have 0 plus 9 over 4, which is 9 over 4. So I'll just have this here. Okay. And so now from that, we know that r plus 3 over 2 quantity squared is going to be equal to 9 over 4 minus 9. Okay. And remember that this 9 here, if I want to write this as something divided by 4, it will be the same as 36 over 4. And of course, this is r plus 32 quantity squared, which is equal to, if I do 36 minus 9, that should be a minus 27. And that, oops, not over 36. It should be that over 4. And so from here, if I was to take the principal root of each side, then I know this will be r plus 2, and this is plus or minus square root of negative 27 over square root of 4. And the square root of negative 27 here, we know is going to be an imaginary number, and it's going to end up being 3 times square root of 3i. And that's because 9 times 3 is 27. If I do square root of 9, that's 3. Square root of 3, I just keep it that way. And of course, since this was negative, I know that square root of negative 1 here is just I. Okay. Oops, sorry. I'll write that here. So that's how that ends up becoming that way. So, of course, here, this is square root of 4 is just 2. So finally, I know that once I have this equals this, my final answer here, if I subtract 3 over 2 from both sides, would just end up looking like this. Okay. And I could rewrite this as lambda plus or minus omega I, which lets me know that my lambda is negative 3 over 2. My omega is going to be 3 times square root of 3 over 2. Okay. So in this case, we see that we have these two roots that are complex conjugates of each other, and we have this root that's by itself. Now, each of these roots refer to a particular general solution here. We know that r equals 3 in terms of our basis of solutions here. So our basis of solutions, this one is only going to produce 1, which is going to be e raised to the 3x. This one, though, will produce 2, and we know that in general, it's going to be e raised to the minus 3 over 2 plus 3 root 3 over 2 I, and then of course we have the same one with the minus. Okay. However, we know that this is not useful to us, and we instead want to express this in terms of the exponential function multiplied with the cosine and sine functions. And so I'm going to erase this and rewrite what that would look like. All right, so in general, we have this form of e raised to the lambda x times cosine of omega x plus sine of omega x. And of course, I have like constant C1 and C2 here if I was going to do a general solution here. So what this looks like is going to be e raised to the minus 3 over 2x times cosine of 3 root 3 over 2x for one of the fundamental functions for our basis. And the other one is just going to be same thing, but sine instead of cosine. Okay. And so our general solution to this differential equation would just be the linear combination of these three functions here. And so when we do that, that will look as follows. All right, so this would be yx is going to be equal to c1 e raised to the 3x plus c2 e raised to the minus 3/2 x times cosine of 3√3/2x plus c3 e raised to the minus 3/2 x times sine of 3√3/2x. And so this would be our general solution to this particular ordinary differential equation. Okay, so for our next example, we're back to looking at one to where that it requires us to use the rational zeros theorem again. And so for this one, I went ahead and worked it out just because I wanted to show you something a little different and at least give some examples to where you've already seen this worked out so I can just talk through it. Again, I've already talked about using the rational zeros theorem. And to do that, we just use all the combinations of all the factors of this number divided by all the combination of factors of this number, okay? And so here, notice that we're dealing with situations here where we have a 1 down here, but I do want to go ahead and address the fact, let's say if we had a 2 here, okay? So if we had a 2 here instead of a 1, then all the factors down here would be plus or minus 1 and plus or minus 2. And what we would have to do here is to take all these numbers in the numerator divided by 1, then also take all those numbers in the numerator and divide them by 2. And of course, any numbers that repeat, we would take out that second number. So for instance, let's say here we ended up the first time dividing by 1 here, I would have this divided by this would give me 2. But I also know if I do 4 divided by 2, that's also going to give me 2. So since I have 2 2's, I can take one of the 2's away because I really don't need it. Okay. So we would have to deal with that situation like that. Luckily for us, in the examples that we're doing here, our leading coefficient is just a 1, so we really don't have to worry about that. But if you ever get a problem that's like that, then that's how you would approach it. All right, so I'm going to erase all this and then we'll talk about this particular problem. All right, so as I said before, we know that right now we have a 4th order linear homogeneous ordinary differential equation. We know that this is a corresponding characteristic equation for it. And if we take all the factors of 108 divided by all the factors of the understood 1 that's here, then we get this list of possibilities here. And so naturally, we would want to, well, I'll say traditionally, we would want to try all of these out. And here's where we really would want to use the graphing calculator to put that particular characteristic polynomial in it and run through all these numbers. You don't want to try all these out by doing the synthetic division by hand. It's going to take you all day. Okay. So here, I'll say using technology to quickly find out which of these potential zeros are actual zeros, we see that the 2 that actually worked for us here are r equals 3 and r equals minus 4. Okay. So notice that we have, again, a 4th order linear homogeneous ODE, which means we have a characteristic polynomial of the 4th degree, which means we have 4 actual zeros we need to account for. Okay. So here we only have 2 of the 4 of the zeros that we need to account for covered. So because of that, we are going to need to do synthetic division to figure out what are the remaining two zeros, okay? And so as of right now, what we understand from our characteristic polynomial here is that this can be written as, I think this is, make sure, yeah. So this can be r times 3 times r plus 4 times something else. And this is going to be a quadratic expression here. And so we need to do the synthetic division to figure out what this quadratic expression will be. And once we do that, we can actually, figure out from that point what all the zeros of this particular characteristic equation will be, and thus what our basis of solutions for our general solution will be. All right, so moving forward here, if we start the process of doing synthetic division, of course, these coefficients came from the coefficients from our original characteristic equation. This is the first zero that we're trying out. We take whatever number this is, pull it down, and then we do a succession of multiplying and adding. And so we've kind of already gone over that, so I'm not going to bore you with the details on it. But we see that we end up getting 0 here in the remainder box. So this lets us know that yes, r minus 3 is definitely a factor of our characteristic equation. So this means that f of r is going to be r minus 3 times the rest of this. Now, I go and I test to see for r equals 3 if it's going to be of multiplicity higher than 1. So I take what I have here, which is the coefficients for this cubic expression, and I do synthetic division on that with the same 0. Okay. And I notice that whenever I do that, I also get 0 in the remainder box here. So that means that r equals 3 is a 0 of at least multiplicity 2. Okay. Now, that's pretty much all I needed, because from here, regardless of whether I want to do completing the square, quadratic equation, or traditional factoring methods, I can figure out what this is going to factor out to be. Okay. And so it turns out that factoring this is relatively easy. It's just going to be r plus 4 times r minus 3. And thus we see that that r equals 3 root is actually a root of multiplicity 3 and not just of 2. Okay. So we have r equals 3 being of multiplicity 3. And we have r equals minus 4 being of multiplicity 1. Okay. So we see that here. R equals 3 has multiplicity of 3. R equals minus 4 has multiplicity of 1. So since r equals 3 has a multiplicity of 3, if we go back to theorem number 1 again, notice that this says that if r is going to be of root m, so r equals 3 is going to be multiplicity of 3, then that means, or m equals 3, then that means I keep on writing this pattern here for the basis of solutions up until m minus 1, or up until I get to x squared e raised to the 3x. So I will have a x e raised to the 3x and just an e raised to the 3x in my basis of solutions here. And so this is exactly what you see me doing right here. Okay. Now, of course, for the r equals negative 4, since it's a multiplicity 1, it only has one corresponding fundamental function for it, for the basis, and that's going to be e raised to the negative 4x. And so now my general solution is just going to be a linear combination of all three of these plus this one here. And so I see that because of that, my final result here would just be, of course, a linear combination of the first three plus the last one, where of course C1, C2, C3, and C4 are just real number constants. So for our last example here, we're given the fact that we know that this particular quartic expression can be factored into this particular expression here, where we have basically two complex expressions that are squared. And using that information, we want to find a general solution to this fourth order linear homogeneous ODE. Now, if you notice here, since this is fourth order linear homogeneous, our characteristic equation here is essentially going to be r raised to 4 minus r cubed plus 14r squared minus 20r plus 25 is equal to 0, which on the left side of that equation is essentially what we were given here. Because of that, we know that this expression here can be factored into what was given to us, okay? And so this is an example of, we see that we have a polynomial to where when we try to factor it out, or if we wanted to find the zeros, all the zeros will be complex. And so since all the zeros are complex, we're not going to be able to use a rational zeros theorem to do it, okay? And so that's why for this example, since this situation is actually kind of hard to find from here, that's why we just give it to you in the problem. All right, so we have this expression here. And so what this means essentially is that, of course, both this factor and this factor is going to equal 0. And I'm going to skip a step here and just basically say, all right, well, what this means is that r minus 1 minus 2i is equal to 0, or r minus 1 plus 2i is equal to 0. Because we know, even though both of those complex factors are squared, essentially what's important is what's on the inside here, okay? So from here, if we look at this first one, then what this is basically telling us here, if I was to basically write everything out, this would be r minus 1 minus 2i if I get rid of the parenthesis there. And did I write this correctly? Yes, okay, so I used the first one here. Just trying. All right, so we'll just do this, and then for this one, I'll get rid of the parenthesis there. We'll do this. So here, if I was to add 1 and to add 2i to both sides, then r would just be 1 plus 2i. Over here, if I did similar, add 1 to both sides, subtract 2i to both sides, we would have 1 minus 2i. And of course, these are conjugates of each other, okay? So now that we know what our two roots are, let's not forget that both of these roots came from factors in our characteristic equation that both had a multiplicity of 2, okay? So here we know that this comes from, this root is going to be of multiplicity 2, and this root also comes, is multiplicity 2. Now, in general here, I'm going to come to the side. So remember, whenever we had roots are of this form, plus or minus omega I, that the general solution for things like this, if we just had these two here, would just be e raised to the lambda x times c1 cosine of omega x plus c2 sine of omega x. So that's what it would be in general. However, each one of these roots here has is of multiplicity 2. So for this one, if you remember, the complex root that is the lambda plus omega I, that went along with the e raised to the lambda x times cosine of omega x, okay? And since this particular root has multiplicity 2, what that means is that I also have another fundamental solution of e raised to the lambda x times x cosine of omega x, okay? So I actually, since it's a multiplicity 2, I got to have this one and this one, okay? Or I know a lot of people would like to write the x in front here, and that's totally fine. As a matter of fact, I think I'll do that to make it look a little better. All right, so we'll just say x e raised to the lambda x here. So that would be my basis of solutions for this particular root, and similar thing would happen here. So I would have e raised to the lambda x sine of omega x as 1, and then of course same deal here, but I would have an x out in front, and that would be the basis of solutions for this particular root here, since it is of multiplicity 2. And so remember that theorem 3 is where this actually came from. So if you remember, if we had our roots being lambda plus or minus omega I, and we know from theorem number 2, if we had complex root r of multiplicity m, then we would have to, list everything according to how we saw here. But remember that the complex form of this wasn't useful, and so that's why we said instead we'll express this in its sine and cosine forms times the exponential expression e raised to the lambda x. And so since this is of multiplicity 2, our roots are, then we use this one and this one for the lambda plus omega I, and we use this one and this one for the lambda minus omega I. And so that is where I'm getting all this from. And so now that we kind of see where everything comes from, we can simply state that our general solution is just going to be C1 e raised to the lambda cosine of omega t here, plus C2 x e raised to the lambda x cosine of omega x, plus C3 e raised to the lambda x sine of omega x, and plus C4 x times e raised to the lambda x sine of omega x. And of course, if we wanted to get a little fancy here, we could simplify this a bit and just say that this is going to be C1 plus C2x times e raised to the lambda x cosine of omega x, plus here was it C3 plus C4x times e raised to the lambda x sine of omega x. So either one of these forms is okay as far as what your final answer is for your general solution to this particular differential equation. So this is the last example, and hopefully these examples sort of give you a basic idea of how to deal with higher order, nth order linear homogeneous ODEs when all the coefficients are constant. Take care.